Okay, let's go ahead and start the class. A couple of announcements. Your homework 4 will be posted today. Homework 5. This is the last homework. Will be posted today, okay, or tonight, right? It will be 3 or 4 questions on chapter 5. So I'll try to make it short, as short as possible. And it will be due Saturday night. So let's do Saturday, end of the day, 11:59 p.m. on Saturday. Okay. The reason it is due on Saturday night is because you have the exam on Monday, and I want you to have access to the solutions of this homework at least more than a day before the exam. Okay. Which this opens the way for the second announcement, which is Monday, April 21st, right? 19th. April 19th is exam 2. And also, as you all know, we didn't have a class on Wednesday. I'm pretty sure you got my email. I couldn't come in. And I wanted to post the lecture on Wednesday on the video during the weekend, so you can watch it before coming to class, and then just solve example problems this Monday. But then I decided it's a better idea to come to class and do the lecture live, right? So I can answer your questions and all of the problems. And we will solve example problems for exam 2 on Wednesday. Okay, so all of Wednesday will be dedicated to solving example problems for the exam 2. What I'm going to do is I'm going to send you a couple of problems before the Wednesday, right? Like 30 minutes before the class. I will also try to bring printout to the class, right? So you will get a feeling of how many questions are going to be on the exam, what are the type of the questions you are going to see on the exam too, okay? And then for the class we missed, for the last week's class, what I'm going to do is I'm going to have an online class sometime between after the exam 2 and before the final exam, right? We can decide on the time together, right? You don't have to be present in that class. It will be online. Or if enough people want to show up to class, we can always come in, so have time to come in. And that will be a final exam review, okay? It will review all of the course material. Final exam is a comprehensive exam, so it will be from the start of the book until the end of chapter 5. Okay, 5 whole chapters. Inviscid incompressible aerodynamics. And yeah, I guess that's it. Is there any questions about these deadlines, the due dates, and how the classes are going to be structured? I don't remember off the top of my head, but I think it was April 29th. It is on your syllabus. Let me double check. $578. Spring 2021. April 28th. Yeah, that's April 28th, 4 p.m. Final exam. Let me write it down here. I will double check the exam time and date to make sure it is the correct date, but I have checked it like a couple of times. I think it's the correct date. April 28th, 4 p.m. And when the time comes, we will talk about how the how many questions we're going to get on the final exam, and all of those fun things. Okay? So this Wednesday, we will do a chapter 4 and 5 review. If you have any questions on chapter 4 and 5, make sure to ask them. We will solve a couple of examples. And we'll solve a couple of examples. And on Monday, we will have the exam 2. Wednesday is a wellness holiday. There won't be any classes. I may actually do the online class on Wednesday, final exam review. But since it's a wellness holiday, I mean, the final class, we don't have mandatory attendance policy. You can always watch the lectures later and submit your attendance. So attendance is never mandatory at that specific time. Okay, and the last class, which is going to be Monday, April 26th, will be dedicated to graduate student presentations. Okay, but we have 6 graduate students who have registered for the face-to-face part of the class, and we have 8 online students. I don't think we're going to have enough time for everyone to present live during the class. So what I'm asking graduate students to do, I haven't told them yet, but I'm telling you right now, people who are a part of the face-to-face class, you have to come here and present, right, to the whole class. That's the last lecture. And online students can just submit their presentations to me, and I will share it with the class. Okay. Well, I'm pretty sure we will have a lot of logistic problems if we want online students to present virtually live, right? Our university is not prepared for the equipment and whatnot. So face-to-face people, how many graduate students do we have? We have 1, 2, 3, okay. And but your partner is not here, right? What about yours? Who's your partner? No, I mean her partner has registered for the virtual class.
Oh, okay.
Okay, Matt is here, and we also have John and Tony. Okay, I'll talk to you to set up your presentations. Okay, so we will have on Monday we will have graduate student presentations about their projects. Undergraduate students, if you ask questions, you will get. I wanted to make asking you questions mandatory, but I just decided against it. So if you ask questions, you will get bonus points. Pretty simple. You can just ask the most basic questions and get a bonus point. I think it's a pretty good deal. And yeah, is there any questions?
Are exams going to be formatted like the last one?
We will talk about the specific exam format in a bit. Okay. Is there any questions about the lectures, about the structures, I mean, the time, due dates, and all of those things? No. Okay, so let's talk about exam 2 a little bit. Exam 2. On exam 2, you will get, this is what I'm thinking right now. I haven't finalized the exam yet. But the problem we had in exam 1 was that you didn't have enough time. There were too many questions. And I can accept that. So we are going to reduce the number of the questions. I think that's a logical conclusion from the exam 1 experience. So on exam 2, you are going to get 4 explanatory questions, at least. I mean, the maximum number of explanatory questions are going to be 4. So 4 questions that you don't need to solve anything. You just have to explain a phenomenon, like dawn wash. Depending on how hard the question is, the number of questions this number can reduce to like 3, 2, or 1, right? If there was only 1 question, I may ask you something that we haven't necessarily defined, but you can just explain based on the things you have learned, right? I don't think I'm going to do that, but because it's going to make everything a little more complicated than what it needs to be. Okay, so that's the maximum number of explanatory questions you're going to get. And undergraduate students will get 2 questions they need to solve. One from chapter 4, like problems, numerical, let's call them numerical problems. You have to plug in numbers to get the results, right? Undergraduates. Okay. Graduate students, we get 3 problems. And these problems will be only like undergraduate students will get one problem from chapter 4, one problem from chapter 5. And what I'm going to make sure, just to make sure to keep the exam as short as possible, I'm going to make sure that you don't need more than a page to answer these problems, right? Like problem 1 on the previous exam, you needed at least 2 pages, right? Some people needed 3 pages, depending on how big your handwriting was, right? So I want to keep the problem short and simple. As long as you know the basic concepts, you should be able to answer those questions, right? Okay, does this make sense? Is there any questions now? I think Shelby had one question, right?
I think you answered it.
Okay. Okay, so that's for the the last thing I wanted to discuss was the lecture notes. I will upload the lecture notes tonight for chapter 5. There is one part of the lecture notes. It is called the wing-body interaction. This is something that I wanted to cover in the class, but we didn't have enough time, right? It actually says on the lecture note that this is not part of the course. You can just study if you like. And whoever studies those parts and Google what the wing-body interaction is and submit a like 2-page report. 2-page report on wing-body interaction. We'll get 4 bonus points. So 2% of your grade, which I think is going to bring the total bonus point you could have earned in this class to 20. Yeah, 20 bonus points, which means 10% of your grade. You could have, if you have already submitted all of these, you can bump up your grade 2 letter grades, right? From a C+ to an A. Yes, I think so, yeah. From a C to an A. No, from a B to an A. Yeah, 10%, yeah. Okay, so 4 bonus points. And I heard there is no, if you want to go back and submit the bonus points, you can, if you think you need the bonus points to improve your grades. I usually set a week deadline for the bonus points, but it is not a hard deadline. Right? If you just tell me that I did this one, I worked on this, I want to submit it, I'm not going to say no, right? Because the purpose of the bonus point was for you to learn the material a little deeper. If you have done the work, you'll get the bonus. Okay, it doesn't matter when you did it. Okay. So let's actually, if there is no other questions, let's actually continue the discussion on the flow over wings. If you recall, we were able to calculate the induced angle of attack as a function of y, which was equals to 1 over 4 pi v infinity integral of negative b over 2 to b over 2. That's d gamma dy divided by y minus y naught. Okay, y naught minus y, sorry. And we also, before that, we actually found the induced velocity as w of y naught negative 1 over 4 pi integral of negative b over 2 to 2b over 2 d omega dy and this is divided by y naught minus y again. And we actually show in the previous, it was the last week, that we show that induced angle of attack is actually negative w y naught divided by v infinity. We were able to find this equation first, then we use this equation second to come up with the induced angle of attack. Okay. So we can find the induced angle of attack. The next step for us would be to find that's alpha. Just make sure you are clear on this, not A. Next step for us would be to find the regular alpha, which is the effective angle of attack plus the induced angle of attack. Do we remember these equations, right? I think these ring a bell, hopefully. So we want to find, next step is going to be the geometric angle of attack. Just a reminder, this what's called the geometric angle of attack, which is essentially the real angle of attack your aircraft sees. This is the angle of attack. This is effective angle of attack. And this is the induced angle of attack. That is induced by lift, right, because of the downwash phenomena. Okay. So we are able to find this, but we want to find an equation for the geometric angle of attack. The next logical step is to find an equation for the effective angle of attack, right? If we go back to the analysis of chapter 4, we had this CL versus alpha. Okay. And we said in the beginning of this chapter, we said this for an airfoil. If you want to apply the same, if you want to use the exact same plot for a wing, this will be CL versus effective angle of attack. Okay? And over there in chapter 4, we were able to find an equation for alpha L equals to 0, which was the zero lift angle of attack, right? We were able to find that. So how can we find a random effective angle of attack using CL and zero lift angle of attack? The idea was that CL versus alpha was just a line, right? So as long as you have the slope of that line, which is called the lift slope, we should be able to find any angle of attack or any CL based on that angle of attack. So the lift slope, dCL the alpha, right? Or we are going to use the value of A naught for effective angular is going to be equal to CL minus CL. Let's call it CL2 minus CL1 divided by alpha 2 minus alpha 1, right? Alpha 1 in this analysis is going to be alpha at L equals to 0, right? And alpha, the zero lift angle of attack. And by definition, the lift for that case is 0, right? It is 0 lift angle of attack. So we're going to get CL minus 0, alpha effective minus alpha L equals to 0. Okay? So your CL is going to be A naught, A effective minus alpha L equals to 0. If you rearrange this for alpha effective, which is the thing we are interested in finding, we're going to get CL divided by A naught, whatever that lift slope is, plus alpha 0 lift, right? So we have at least one formulation that is going to help us find the 0 lift angle of attack. But this integral, this other integral, is in terms of circulation, right? You have to have circulation. So it is not. Do you have a question? So it is not a bad idea to try to come up with an equation that gives us the effective angle of attack also as a function of circulation, right? If you have the distribution, then if you have that kind of case, if you have that circulation, you will be able to find your angle of attack, right? You don't need to go and find something else. Okay, let's see how can we relate this to circulation. This part from chapter 4, we already have the equation for, right? So let's say from the analysis of chapter 4, we can calculate. That was dz dx 1 minus cosine of theta, like d theta, whatever, right? As long as you know how your airfoil is, what is the curvature of your airfoil and whatnot, you will be able to calculate that. But this part, CL, we don't have any information on it. Let's see if we can connect this to circulation, right? We define the lift coefficient as lift divided by Q infinity S, right? That's the definition of force coefficient. If it was the drag coefficient, I mean drag divided by Q infinity S. On the other hand, based on the Kuta-Jakovsky theorem, we said lift is rho v infinity multiplied by your circulation, right? And that circulation is going to change. This is lift per unit span, is going to change based on the location on your wing. And keep in mind, again, let's see, actually, let's make sure we are all on the same page. Let's say this is a three-dimensional view of the wing. This is your flow coming through this. You will have wingtip vortices and all of those things. This y actually is this axis y. So we start from 0. Here, it's going to be negative b over 2. That's your span length divided by 2. Here, this is negative b over 2. This is something we discussed in the previous lecture. So we can find the lift per unit span, which is essentially lift at any point, right? Two-dimensional lift. Lift at any point using the Kotar-Jakovsky theorem. We have seen this theorem from the chapter, which chapter was it? Chapter 3 or chapter 2? Right? And we also have this definition. For a two-dimensional case, this will become QL prime divided by Q infinity C. But your chord length, the same is true for your circulation. Your chord length can also change. You may have a tapered wing, right? Which means that this length, this chord length, is also a function of its location in the y direction. Okay? C, y naught. Let's rearrange this for L prime. L prime is going to be CL, Q infinity, C, y naught. Is this clear? Are we clear up to this point? We have all of the equations. We are looking for a new equation for effective angle of attack. And we are moving in that direction. We want to find this effective angle of attack as a function of this circulation. Okay? So these two are equal. L prime, we have two different equations for L prime. So CL, Q infinity, C, chord length at any location is going to be equals rho V infinity, gamma. And this Q infinity is actually the dynamic pressure, if you recall, so which is 1/2 rho V infinity squared. Should cancel with density. This power will cancel it here. So we can write CL as a function of 2 circulation divided by V infinity chord length, right? So what have we done? We have found the dependence of your effective angle of attack based on circulation. Okay? We're going to replace it here to get the final equation. Your effective angle of attack is going to be equal to 2 gamma y naught divided by C y naught V infinity multiplied by 1 over your lift slope plus alpha L0. Again, just to make sure not to confuse this. This lift slope or DCLD alpha is A naught, right? Angle of attack is always alpha, right? Make sure not to confuse these. Okay. So we already know how to calculate the lift slope. That's from chapter 4. And the only other simplification we can do here is the lift slope. Do we know the value of this lift slope from before? What is that value? 2 pi, exactly. So we can replace this with 2 pi from chapter 4. This 2 will be canceled out. This will be your alpha effective. So if you were asked to find the geometric angle of attack, you can find it as a function of circulation. Let me write the general equation here. We have this for the induced angle of attack. We have that one for the regular angle of attack. This is what you're going to get. Alpha is equals to gamma y naught divided by pi V infinity C on y naught plus alpha L equals to 0 plus 1 over 4 pi V infinity integral of negative b over 2 to b over 2 d gamma dy divided by y naught minus y. Okay. This equation is essentially the mathematical representation of the theory that we never mentioned, but we have been using to get to this point. That is called the Prandtl's lifting line theory. This Prandtl's lifting line theory tells us that we can model the flow over wings using horseshoe vortex sheets, a combination of all of those horseshoe vortex sheets. And we have talked about horseshoe vortex filaments, right? Hopefully you remember, everyone remembers those. Okay, so just a couple of quick reminders about the equations that we have seen in the earlier chapters, because this is something that you are going to use for this chapter's problems. Okay. Again, the Kotar-Joukowski theorem is going to give us the lift per unit span, which is the lift at any location in the y direction using rho v infinity gamma circulation at that point. And this is lift per unit span. To find the total lift on the wing, let me actually ask you. We have the lift per unit span. Again, lift per unit span is newtons per meter, right? That's a lift at any point on the wing, right? Just a point. Let's say this is your wing again. Lift here is going to be L prime. Lift here, lift per unit span. Let's lift on this airfoil, right? On this cross section of the wing. But what should I do if I want to find the total lift on the wing? Let's say I have this lift per unit span for each location. How can I use that to find the total lift, L, in newtons on the wing? I have the distribution of, yes? You don't need to model it anymore, right? The idea here is that I already have the circulation needed. So I've used the horseshoe vortex filaments, right, to find that circulation. And I can find the lift per unit span at any location, which essentially means that I have the distribution of lift versus y, right? I have a function for it. What I want to do is to find the total lift. What should I do? Doesn't matter. Okay, so it is definitely not a uniform distribution, right? So we cannot just multiply it by the length. We have to integrate. Okay. Okay.
So I didn't know, could you also just plug in for one point and then the furthest point and subtract?
But that would give you the difference between lifts, right? So what Shelby is telling us is to plug in to find the values at these 2 points, right? And then subtract it. The idea was, if you recall, because of this induced vortices, because of the downwash phenomena, the lift at these two locations is going to be 0 anyways. So the subtraction is only going to give us 0 because 0 minus 0. But in general, if you have the distribution of something, right, over, let's say you have the distributed load, right, from your solid mechanics, right? So you had the distributed load. You wanted to replace it with something else, right? What would you have done? You would have calculated the area under that load distribution. Do you remember this? Hopefully, so there's one person who remembers this. This essentially means you have to take the integral, right? Okay. You wanted to say something? Okay, yeah. That's exactly that what you. So we have to take the integral of negative b over 2, this point to this point, L prime y naught dy. Okay, which essentially means that since we are going to assume rho and v infinity are constant, that's negative b over 2 to b over 2 gamma of y naught dy. And based on the definition of your lift coefficient, your total lift coefficient of the wing, not the lift coefficient of each airfoil, just to make sure that we can make this distinction, because since I'm using the board, you don't see this. This is lift coefficient over an airfoil, right? L prime. So we're going to use a small c for it, a small c. But if you are talking about the lift coefficient of over a wing, which is a combination of all of the lift coefficients over those airfoils, we are going to use capital C. Based on the definition, this L divided by Q infinity S, right? So it's going to be equal to rho v infinity divided by 1/2 rho v infinity squared S. And this is the surface area, total surface area of the wing, integral of negative b over 2 to positive b over 2 gamma y naught dy. And you can simplify this, of course, to 2 divided by v infinity S. Okay, so we can calculate lift, we can calculate CL, we can calculate the induced angle of attack, we can calculate the geometric angle of attack, we can calculate all of those. But we haven't talked about the calculation of the induced drag and the induced drag coefficient yet. If you recall, and if you don't remember this, please go back to the previous lecture and watch it. We said that your induced drag is actually equals to your lift, that's induced drag per unit span, is lift per unit span multiplied by sine of alpha, right? That's alpha induced angle attack. Okay? This is something we saw in the previous lecture, which means that, and I mean, we said that since your alpha of I is small, we can replace this with L prime alpha I, right? Come back to this analysis. If you want to find the total induced drag, just have to take the integral from negative b over 2 to b over 2 to positive b over 2. It's exactly the same idea here. We have the per unit length value. We want to extend it to all of the wing. We just have to take the integral. Okay? This essentially means that your di is going to be rho infinity, negative b over 2 to b over 2, gamma of y naught, alpha I dy. And your CDI is going to be 2 divided by the infinity S, negative b over 2, b over 2, gamma of y naught, alpha I ds. So the difference between the induced angle, the induced drag and the induced drag coefficient, and the lift coefficient and lift, is only going to be the inclusion of the induced angle of attack in your integrals. Otherwise, they are going to be exactly the same. As you can see, even from the equations, that if there is no lift, there won't be any induced drag. This type of drag is induced by lift. Yes?
Where did you get the 2? Like, why did you put it over 2?
Here,
Yeah.
so you just have to come back to this analysis here. It's essentially exactly the same thing. CDI is equal to DI divided by Q infinity S. Okay, Q infinity is your dynamic pressure, 1/2 rho V infinity square. Yes. No. That's the total area. We are talking about the wing values here. Wing induced drag. So that's not the chord length. Total span area, right? Okay. So we have all of these parameters. What we want to do next is to talk about one special case, which is a very important special case, actually. Okay. And that's the special case of elliptical wings or elliptical lift distributions. Elliptical lift distribution. Elliptical lift distribution is going to be the most optimized distribution you can get, lift distribution you can get when you include the induced angle of attack, right? Most of your design is not going to result in real elliptical lift distribution, which essentially means that you are not going to get the most out of your planes because induced drag is going to be higher, right? So in other words, if you don't have an elliptical distribution of lift, your induced drag is going to be higher. This is something we can show based on this integral, but we are not going to go over the proof here. So based on this equation, when we say your lift is distributed like an ellipse, and this is constant, this is constant, this essentially means that your circulation looks like an ellipse, right? So this is essentially means that elliptical circulation distribution, right? Because lift is a function of, is a direct function of your circulation. So let's say this is a front view of your wing. What does an elliptical distribution look like? Of course, it has to look like an ellipse, right? Just to make sure you are not confused, this is a front view of the wing. So what you want to do, and this is something you will do on the homework and you will probably get to do on your exam as well. I will give you a specific distribution. I will ask you to calculate the induced angle of attack, all of those other parameters, the induced drag and induced lift, right? All of those. What we want to do is to find an elliptical, the first job is to find the elliptical circulation distribution, this part, right? And that plug that into the equations we have, and based on that, calculate lift, drag, induced drag, all of those other parameters. Okay. So how would an elliptical circulation distribution look like mathematically? To answer that, you first have to understand what's the equation of an ellipse, right? Because to put it simply, we are interested in an equation of ellipse like this. We are only interested in the top half of it, right? That's ellipse, right? And on this axis, we have circulation. On this axis, we have y, distribution of circulation over y. So we have to have the equation of the line for an ellipse. Who remember what was the equation of the line for an ellipse?
Here it could be circulation in power of 2 divided by A plus Y.
Let's call this length y naught, and this length, yeah, this length b over 2. This is b over 2. Gamma naught and b over 2, right?
So it could be circulation in power of 2 divided by circulation naught. Yeah, plus Y in the power of 2 divided by B by 2
That's square
equal to
1, right? Yeah, thank you. So for your circulation to be elliptical, this equation must hold true. That's the equation of ellipse. Okay? So we can play with this equation a little bit to find the circulation as a function of y. So let's do this. It's going to be gamma naught, a square root of 1 minus, I'm going to move these two to the top, 2y divided by b squared. So your circulation, the changes of circulation with respect to y has to follow this function. Okay? Okay. So we have this function. What we can do is to plug this into all of the equations we have and find like the value of induced velocity, for example, like induced velocity. How can we find the induced velocity? What was the equation for it? Who can tell me what was the equation for induced velocity, W? That's 1 over 4 pi 1 over 4 pi integral of negative b over 2 to b over 2, right? Y minus 5. Okay. So the first step for you is to find d gamma dy, right? How can we find? Yes. Yes. Thank you. Becomes positive when you are dealing with alpha. Yeah. And that's y naught over minus 1. I'm not very good at memorizing these equations myself. Just make sure. Yeah. Okay. So you have to find the derivative of gamma with respect to phi, and which is just taking the derivative of this function, this is a square root function, and you just plug it in. You will be able to take the derivative. Okay. Just keep in mind that value of gamma naught is actually going to be the value of gamma at y naught equals to 0, right? In the middle here. That is going to help you a lot. So you can just plug in y naught equals to 0 and then do all of the calculations. I'm not going to go over the calculations. I'm just going to give you the final results for all of this. So induced velocity is going to be equal to negative gamma naught divided by 2b and alpha I. Since you have already done this calculation, you don't need to take the integral again. we can just use the definition of induced angle of attack, which was the induced velocity divided by v infinity, right? You plug that in, you're going to get gamma naught divided by 2 b v infinity. And your lift coefficient, your lift is going to be equal to rho v infinity integral of your circulation, right? This. So negative b over 2 to b over 2 gamma naught square root of 1 minus y divided by all of this dy. You can take this integral. Your lift is going to be, your final lift is going to be rho v infinity gamma naught b divided by 4 pi. And you can actually find the value if you were given lift, the distribution, or your total lift. If you were told that the lift for this wing is measured to be whatever, you can find the calculation the value of gamma naught based on that equation, just rearranging that equation using this equation is equals to 4L divided by rho infinity v infinity b pi. You can, if you have the value of CL, you can actually play with this to get the same equation as a function of CL divided by b pi. Okay. So is there any questions? Are we clear? You just have to plug in the values. You really had to take the integral twice. Once here and once for the induced velocity. And then you would be fine. Okay. But here we have the induced angle of attack as a function of gamma naught. If we want to have it as a function of CL, you can just plug in gamma naught over there. I'm just going to use this value for gamma naught, SCL divided by B pi, divided by whatever we have over there. That's 2BV infinity. 2BV infinity. So the V infinities will cancel out. The 2's will cancel out. You're going to get SCL divided by pi B squared. Right? Can we simplify this any further? Just look at the S and B squared. What does this remind you of? Aspect ratio, right? Or 1 over aspect ratio, to be exact. We define the aspect ratio for a non or for a general wing as B squared divided by S, right? Here we have S divided by B squared. So your alpha I is actually CL divided by pi aspect ratio multiplied by the aspect ratio of the wing, which is also a design parameter. Okay. So we have alpha I. How can we find the induced drag coefficient? What was the relationship between the induced angle of attack, and the induced drag coefficient. Just the induced drag coefficient. You can actually bring the CL. That's what I'm referring, right? That's the induced drag. The most simple relationship you can find is this, right? The induced drag is equals to lift multiplied by alpha I. You can actually write this in terms of the coefficient CD alpha I, CL, I'm sorry, CL. Let's plug alpha I over here. So CD and I, or CDI, is going to be CL multiplied by CL divided by pi AR, which means induced drag coefficient is CL squared divided by pi AR. This is the most commonly used equation when it comes to the calculation of the induced drag. CL squared divided by pi AR, which tells you that your induced drag is directly related to your lift coefficient, right? And inversely related to aspect ratio. As you increase the aspect ratio, your induced drag is going to become smaller and smaller and smaller because you are getting closer to the infinite wing formulation, right? Okay, but as I said, we can actually show that the most optimal solution you want to get is the elliptical solution, the elliptical lift distribution. Optimal, the most optimal solution. This is the most optimal solution you're going to get. Okay, the elliptical distribution. How can we get this distribution? We have to have an elliptical wing. So the shape of your wing is going to directly dictate your circulation and lift distribution. Okay, so if this is the minimum we can get, what we can do is we can introduce an efficiency factor, which is between 0 and 1, right? Efficiency factor that comes into play in the denominator, right? CL and I is going to be equal to CL squared divided by pi E AR, okay? This efficiency factor for an elliptical wing is going to be equal to 1, right? Which is going to give you this equation. The least amount of induced drag you're going to get for a specific lift coefficient and a specific aspect ratio, right? As you change the shape of the ring, the wing, as you get further away from an elliptical wing, your efficiency factor is going to decrease. What does this mean for induced drag? Since you are multiplying this whole thing by a number that is less than 1, which means that this whole thing is going to increase, right? Which means that your induced drag is going to, this is CD and I, just to make sure, is going to increase. Okay, and one thing that people still do is to compare the induced drag they get from the wing based on the lifting like Prandtl's lifting line calculation, all of those integrals, right? They find a CDI using this formulas, right? Then they calculate the lift coefficient divided by PAR to find the efficiency factor of that specific wing. Okay, does this make sense? Yes. Not all of them, no. All of these equations are very general, right? The equation we have here. But these ones are only for elliptical wings, right? Because we already have the distribution of circulation. For these equations, see, we say gamma of y. We don't know the distribution. We're just using a value, whatever distribution. It can be any distribution. Okay. Is there any questions? No. Okay, that's all. So one last thing we want to talk about is the difference, or what's going to happen to your CL versus what's that? Angle of attack, yeah. So what we said was the CL versus angle of attack you calculate for airfoils in the real world, in wings, is going to be giving you the CL versus the effective angle of attack, not the real one, right? Not the geometric one. This is going to look like this: the alpha naught, or the A naught. That's the lift slope, DCL d alpha is going to be equal to 2 pi. This is a calculation we have done in the chapter 4 parts of the class. Okay. And what we want to know is that what will look like if we wanted to get CR forces versus alpha for the finite wing, or if you want to use the geometric angle of attack, which is the angle of attack you can actually measure, right? Geometric AOA, angle of attack. What would it look like? Or what would be the lift slope here? This alpha is actually the effective angle of attack plus the induced angle of attack, right? That's the idea here. And it is going to be looking very similar. So we will have a linear range. We will have the stall condition. But you are going to get less lift coefficient during a stall because you're losing some of the lift to drag, right? The induced drag, because of the downwash phenomena, right? You're losing some of that pressure difference. So it is going to be having a smaller slope. Let me actually make sure to, let's say this is for your airfoil or alpha effective. This is going to be for your wing, this one, or your alpha geometrical, alpha geo. We can actually find the relationship between these two slopes, and eventually I'm going to call this a slope A. And as I said, this slope is A naught. The relationship between the two slopes we can show that is equals to A naught divided by alpha 1 plus A divided by pi E AR. And A naught. In our case, using for a thin airfoil, A naught was 2 pi. You can just plug it in and find the new lift slope based on your AR. Okay. But in the let me just clear something out, and then I guess we'll be done. you will probably, what you're going to see is that this efficiency factor is also sometimes represented by as 1 divided 1 plus delta Oswald efficiency factor, or 1 plus 1 divided by tau. Right? They're going to represent different things, but for your case, we're just going to assume all of them are the same. Okay. I wanted to have a discussion about delta wings, but I don't think we're going to have enough time for it. The discussion is included in the notes, so you are always welcome to go and read this discussion. And the last thing we want to do is the attendance quiz, right? That we have been doing for the past week, 2 weeks. Attendance quiz. Okay. I'm going to ask you to solve example 5.3, or let's actually do 5.1. Let's do this first example of the chapter. We are told to consider a finite wing with an aspect ratio of 8, a taper ratio of 0.8, so a finite wing, aspect ratio of 8, taper ratio of 0.8. What is it? Taper ratio, tau of r, right? 0.8. And the airfoil section is thin and symmetric. So we are dealing with thin airfoils, which is our forte, hopefully. Thin and symmetric. We want to calculate the lift and the induced drag, lift coefficient and induced drag coefficient. For the wing, when it is an angle of attack of 5 degrees, and we are going to assume that delta is equals to tau, which means that you'll see that I told you. So E is equal to, again, 1 plus delta, efficiency 1 plus tau. Tau here is equals to delta, and its value is, what's the value for it? 0.1. No, that's a taper ratio, 0.8. Tau is equals to 0.105. Okay. So, what should we do? I gave you the wrong tau. That's 0.05. We want to calculate CL. We want to calculate CDI. And that would be it, right? I'm going to give you 5 minutes, which is until the end of the class. And then we are going to solve this. And whoever you We have had the same deal for the past 2 weeks. Whoever can give me a correct answer or something that resembles a correct answer will get a bonus point. And if not, you will just get your attendance check. Let's actually forget about the bonus point and let's solve this together, because I don't want anyone leaving the class after the class is done and not seeing the solution. Okay, so let's see if we can conclude anything based on what we are given first. All of these are numbers except for 2 words. It is a thin airfoil, which is telling us we can use the analysis of chapter 4 and chapter 5, right? And the other one is symmetric. The airfoil is symmetric. What does this tell us? Or does it tell us anything? It's just a nonsensical word. It doesn't mean anything to us. What does this mean? A symmetric airfoil. So Muhammad is telling us that this means 0 lift angle of attack is 0. Right? Is this true? We have one person saying yes. What about the rest? What about the rest of the class? Do we remember this, right? If you recall, we said that CL versus alpha for a symmetric airfoil starts from here, which essentially means that at 0, this is a symmetric airfoil. If you have 0 angle of attack, pressure distribution on the bottom or on the lower surface and the upper surface are the same, right? Which will result in 0 lift. Okay, so symmetric, this is what it's going to tell you. Okay. What else do we have? We have the value of the angle of attack. Okay. So your CL versus alpha is going to look like this. We have 5 degrees. We want to find the value of CL. What do we need here? We have 1 point, 0 and 0. We have 5. We want to find CL. We need the lifted slope. Exactly. How can we find the lifted slope? This is CL versus geometric angle of attack for a finite wing. So we have to use this equation to find the lifted slope, right? Since we are also told that we are using a thin airfoil, so we already know A naught for a thin airfoil, right? We already know that, yes. Yes, we do. This A naught for a thin airfoil, is essentially 2 pi based on chapter 4 calculation. A naught is the value of this slope for an infinite wing, right? That's the discussion. So since we are told that this is a thin airfoil, we can just plug in the values there. A is going to be equal to 2 pi divided by 1 plus. We just have to plug this value of 0.055 here. to calculate the efficiency factor, right? Or we can just include it here, that it is going to be equal to 2 pi divided by your aspect pi aspect ratio multiplied by 1 over e, which is going to be equal to 1 plus tau. Okay. Just make sure that you understand the difference between the taper ratio and this efficiency factor here. Taper ratio was the tip chord divided by the root chord. And here, this is just extra information to throw you off your game, right? Tip chord divided by root chord. You actually use gamma. I don't remember what we used. Some people use tau of r, some people use gamma for it. So here we don't really need that taper ratio. So this is 0.055. We have the aspect ratio to be 8. We have the pi, we have the value, we know what 2 is, and we also know what 1 is. If you plug in all of these numbers for A, you are going to get 0.087 per degrees. Per degrees. That will be the unit. So we have the lift slope. How can we find this lift using that lift slope? Lift slope, based on what we are seeing here, is going to be CL minus this 0, right, divided by alpha, which is 5 degrees, minus 0 lift angle of attack, which in this case is 0. Okay? And we also have the value of A. So if you plug that in, your CL is going to be equal to 0.4335. Okay, we have CL. We want to find the induced drag coefficient. How can we use CL to find the induced drag coefficient? What was the equation over there? Induced drag coefficient was equal to CL squared divided by pi EAR. Since we are given tau here, or delta, can actually plug that in. E is equal to 1 over 1 plus tau. If I put that in here, it's going to be CL squared multiplied by 1 plus tau divided by pi AR. We have all the numbers there. We don't need to do any calculations for anything except for plugging in the numbers. If you plug all of the numbers in, your induced drag is going to be 0.00789. And that's it. Yes.
When you were explaining earlier about the symmetric versus the angle of attack being equal to 0, but I thought the angle of attack was 5.
No, that's the 0 lift angle of attack is 0. That's alpha L equals to 0. You remember that variable? We had an angle, a specific angle of attack at which lift was 0, and we had all of those integral equations for it, right? You remember? That's negative 1 over pi integral of dz dx 1 minus cosine of theta, right? From chapter 4. That's where the angle of attack is 0. That's where lift is 0. Angle of attack where lift is 0, right? For a symmetric airfoil, that angle of attack is 0. Okay? Yeah, 5 degrees is the degree that we are already flying at. So that's it for today. And we'll see you on